regular fragment of resolution of parity. Let's start from the definition. Proof lines in the resolution of the parity are linear clauses. These are just a disjunction of linear equations modulo 2. And it is important for us that linear clause is just a negation of linear system. If we consider two rules, resolution rule, just we can resolve two linear clauses if we have the same linear form, but with different right-hand side. And weakening rule, by weakening rule, here we have semantic weakening. We just can do anything that follows. Refutation of a CNF formula phi is a sequence of linear clauses such that the last linear clause is empty clause, and every other is either represented the clause of the formula or is obtained by the roots. Now this is the extension of resolution, and it's rather easy to see that in this proof system, unsatisfiable of two linear system are easy. That is not true for resolution, and the matching principle for graph without numbered vertices, for example. And this proof system is a subsystem of AC0 fragment with modulo 2 gates. And this is a major open question to prove lower bound for this. And nowadays, even for resolution of parity, lower bounds are unknown in a restricted version. Okay. For the latest, I need the notion of linear branching program. Linear branching program is just an extension of plain branch program, but here we branch on the value of linear form instead of value of variables. It's one, the same as usual. We have sinks of the graph, and on sinks we have results of branching program, the standard thing for every CNF formula phi, we have associated a search problem. Given a satisfying assignment, given an assignment, we search for clause falsified by this assignment. There is very standard that every refutation can be considered as linear branching program. For this is a rather standard way. Just it will be important for us how to do it. We first of all construct all weakening rules, and now we assume that we apply weakening, and then after it we apply resolution rule, assume that clause A is obtained from B and C, and B is a weakening of A equals to 0. No. A or equals to 0 is weakening of B, and A is 1 weakening of C. Then in a branching program, we will split here on F, and here this H will be equals to 1. This equals to 2. Okay, and since are already labeled with a clause of initial formula because it was a proof. The important property of such program, if we consider some path from empty clause or the source of the branching program, not necessarily from the source, but from any clause E to clause D. Then the negation of E and the linear system on this path semantically implies negation of D. This can be easily proved by induction. And for example, if we start from the source, then we just know that the linear system implies negation of the clause. Okay. What is known? There are a lot of lower-bound for tree-like case, a lot of different techniques, and in tree-like case, the refutation is equivalent to parity decision trees. It's a partial case of linear branching program when the graph is a tree. Okay, and we proved the first lower bound for something that is strictly stronger than tree-like case, the regular. First of all, we start with a just regular resolution. I recall it. For regular resolution, for every clause, we store also the set of variables that was used in the resolution rule in order to derive this clause. And it is allowed to derive, to apply resolution rule only if on variable x, only if this variable does not belong to the union of variables to these clauses. And we essentially naturally extended to resolution of a parity. Now we store the list of linear forms, and we say that it is allowed to resolve clauses C and D on the form F if F doesn't belong to the union of linear span of LC and L. It is known, no, it is not hard to show that regular resolution of a parity simulates tree-like resolution, and it is straightforward that it simulates regular resolution. And it was known before that regular resolution, plain regular resolution, can be exponentially stronger than tree-like resolution of the parity. Thus, this proof system is strictly stronger than tree-like resolution of the parity. What we have in linear branching program for regular case, consider some node V of branching program. We find post V as linear span of all linear forms that are below V. We remove regularity here is that linear form that corresponds to the V is not it doesn't belong to post W1 and W2 for the child. And in fact, the only property of regularity that we use is the following. If the node V is of the distance T from contradiction, then dimension of post V is less than the maximal dimension on at least T. Well, it's easy to see that during this path, the dimension decreases at least by one every each. This is the only thing that we use for in our lower bound. Okay. And now let's formulate the main result. First of all, hard formula. Hard formula is a binary pigeonhole principle that states that there exists m distinct binary strings of length L. And we alternatively say that x1 is address of the whole of the first pigeon, x2 address of the second pigeon, and so on. And variables xig is the jth bit of the string xi, and clauses how it is encoded in CNF for every pigeon ai and every address a. We say that either xi not equals a or xj not equals a, and this is just a plain clause. And our main result is that any regular resolution of the parity refutation of binary pigeonhole principle has exponential size. And here m And let's start from the high-level overview of the proof. High-level overview is the following. We consider regular refutation. We represent it as a linear branching program and start a random path in this program. And this path looks as follows. We just take a random full assignment and make t steps from the source. T is cubic group of the fan. And let C be a linear clause at the end of this path. First part, we claim that the rank of negation of this linear clause is high, with probability at least 1/2. And it's not easy to understand that it is okay. It is all because the random assignment sigma satisfies linear system, stable linear system with rank R with probability exactly 2 to the minus R. And hence we necessarily will have a clause with actually its negation has large rank, and each clause can be used with exponential small probability. So we should have exponential number. Okay, this is very hard, and let's do in slightly more details how we prove rank our bounds. We will define the notion of locally consistent of linear system, and first we prove that not C is locally consistent with probability at least 1/2, and the second we prove that if not C is locally consistent and T is the distance in linear branching program from the source, then rank should be high. We will start from the definition of locally consistent and from the second part. Let phi be a linear system over variables of binary pigeonhole principle, and assume that it has rank T. We say that this linear system is locally consistent if for any T+1 pigeon there is solution of the system that injectively sets all other pigeons except this T+1. Okay. And the lemma is the following: that assume that negation of a clause C is locally consistent, and there is a path from linear branch program from empty clause to vertex where V is of length D. Then the rank is large. And this lemma can be proved by the following. So first of all, assume that our resolution of parity proof, the clause C is derived from the set of clause A. And assume that the set of clause A mentioned exactly n+1 minus R pitched. That's R, exactly R pitched are not mentioned in that set.
What is the L in this statement of the lemma?
L is can.
Oh, okay. L is yeah. Okay. Yeah.
Okay. So A not mentioned, and first of all, we prove that if negation of C is locally consistent, then rank is at least R. It is good if R is large, but bad if R is small. But it just follows from the definition of locally consistent. Let K be the set of pigeon that are not mentioned in A. Size of K is R. By assume that rank of negation of C is less than R, then by locally consistent there exists a solution of not C that sends all pigeons that are not in K in different holes. Hence, sigma satisfy all clauses from A because they not mention pigeons hence, since C is derived from the set of clauses A, sigma should satisfy also C. But sigma is a solution of negation of C. This is a contradiction. Okay. And now the second case, then give lower bound and R is small. Assume that dimension of post V is a vertex where C is a differential program. That dimension of post V is less than maximal dimension. Okay, and this is a case because our proof is regular and we know this product. Then rank of negation of C is at least T minus R times N.
What is T? You said that it's not
T is the distance between empty clause to the clause C in some path.
how much? What would be the
Cubic root of n. Okay, and to prove this claim, we consider the following vector space. We consider all linear forms that are clause C, and also all linear forms below post of V, and consider span. And let us estimate the dimension of this. The first estimation is trivial, is null by the definition of this linear space. It's the most rank of C plus dimension of post of V, and by our assumption, this is the most. Okay, but now we also can estimate it from below. Why it is so? Because what is n plus 1 minus r? It is the precise the set of pigeons that are mentioned in A. But the formula of bit pigeon hole, if we the clauses of bit pigeon hole, if we mention one pigeon, then we mention L variables associated with this pigeon. Okay, for every element of A, there is a path to vertex V, and we know that this clause should be implied from negation of C and linear system on this path. No, that means that all variables from this clause should be in this V. So we lower bound V from below, and from this we get what we want. And so we have to lower bound, and we can combine it by multiplying the second one by L and adding. And now we have lower bound on the rank of negation of C. Okay, but we should have somehow show that the linear system is locally consistent. And how it can be done? The idea is the following. We consider a matrix whose columns are indexed by variables of bit pigeon holes. We say that this matrix is nice if there is a basis in the set of columns of this matrix such that for every pigeon we have at most one column in this basis. We say that such matrix is nice. For every pigeon, we have at least one column in the basis. And the linear system, is nice if it's satisfiable and its matrix is nice. The key idea is that to construct a solution of nice linear system, we can choose arbitrary values for all bits, but these bits corresponding to this basis. And after it, the bits of elements of the basis are uniquely determined. Okay, and using this, we can show that a system is locally consistent as follows. Assume that phi be a linear system with small enough rank, and let rho be a partial substitution defined on the set of pigeon A, such that A is the most rank and rho is injective on A. And assume that the system after this substitution rho is nice. No, for example, we can do this. Then the system phi is locally consistent. And this is rather easy. What should we do? Okay. How to show that it is locally consistent? Consider some set of pigeons of size t plus 1, and A minus k is upper A prime, and these pigeons are already assigned by rho to different nodes. And T is a set of pigeons that corresponds to basis in the nice matrix of phi substituted by rho. And here we will choose two holes that differ exactly one coordinate that corresponds to the column from the basis. And all other pigeons except k, for them we choose just distinct rows from there. And for nice matrix, we don't have any restriction here. What we require that all these poles are different, what we choose so far. And it is possible to do this because we have, first of all, A prime we choose, T prime we choose 2, and for Y prime 1, and from our parameters is enough number of holes. And how to show that it's possible to choose 2 holes, just choosing in one by one, and this inequality implied that we can do it for all T prime. And now recall that we want to show that we should have local consistency with high probability. And instead of this, we should somehow define what is the pigeon A such that we can substitute it injectively, and after we eat, we will have a nice matrix. Okay, and for this, we need the following definition. We have a set of linear forms, variables of pigeonhole principle, and we say that this set of linear forms is dangerous if the dimension is more than the number of mentioned pigeons. For example, this set is dangerous, and we say that set of linear form is safe if its span does not contain any dangerous set. And the nice theorem said that a set of linear forms is safe and linearly independent if their coefficient matrix is nice. I will not prove this theorem, but improve the use extension of Hall's matching theorem for matroids. And the next notion is how to find this magic set of pigeon A that after it will be nice. First of all, we need a notation. Linear form minus S means that we delete variables from S from this linear form. And the closure of the set of linear forms is an inclusion minimal set of pigeons such that if we delete variables from corresponding to pigeons from S, we get a safely safe set of forms. And the closure for this example, for this closure is 1 and 3, region number 1 and 3. The properties are quite natural. First of all, it's unique, and we denote it by closure value. It is monotone. If just has the same span that we have the same closure, and the size of the closure is at most the dimension of span of. Okay, so it is good if we can make such substitution to the closure. Okay, and now the last connected. This is in random walk lemma. We should show this high probability when we make random step. We will finish with a closure. We is locally consistent. But now we understand that it is sufficient to show that this sigma, this random, is injective on the closure with good enough probability. And here we can use lemma, and we'll go to this local system. And moreover, if we consider some path and length fi, ti will be linear system corresponding to I step in this path. And since t semantic implies negation of C, then closure of LFC is the closure of f phi t. And hence it is sufficient to show that the probability of that sigma is injective on this closure is 1/2. And now it is not very hard to do, but I think that the lunch is more interesting than the rest of my talk. No, that's main idea I already said, that we can estimate not very hard. Okay, and very recently, using our technique and lifting, it was proved that resolution of parity is strictly stronger than regular resolution, and open questions, except proving Oberwolfach and restricted, is consider another version of regularity. For example, the most interesting for me is the case that in all paths, all linear forms are linearly independent.
We are really short of time, so I suggest we take questions over that and have.
We need